I want to now look at an application of buffers, one that applies typically in the field of biochemistry. That topic is buffers as they apply to proteins. Now, we talked a little bit about proteins earlier in the semester, but in case it's been a little while, recall that proteins are polymers made out of amino acids. So those amino acids have a carboxylic acid functional group, a side group, and an amine group. We saw back in chapter 6 that amino acids can undergo an acidification reaction, also called dehydration synthesis, that allows them to form long chains. Now, looking at this structure, you might first be tempted to say, well, this side is an acid and that side is a base, so this thing might behave like a buffer because of its amino acid structure. And an amino acid on its own does behave that way. However, remember that by the time we've made this into a protein, the polymerization process that occurred wound up removing the sites on either side that would be particularly, for instance, acidic. However, what I want to now draw your attention to are these side groups. There are an array of possible side groups, a variety that are naturally occurring, as well as a whole plethora of artificially created side groups. And many of these side groups can be acidic or basic in character. Included among those side groups, in fact, are side groups that are either amines or carboxylic acids. So that means that our big complicated protein structure, and these protein structures can indeed be quite complicated. They might have, for instance, beta sheets or alpha helices and all kinds of overall potentially complicated structure can be studied along their surface with a variety of groups. And by the way, I'm just drawing these generally coming off a protein, not specific to any particular region at the moment. These side groups coming off can be acidic or basic. However, because they have chemically different structures, they have different pKa values. So the pKa of an amine might be near something like 11, while the pKa of a carboxylic acid might be closer to something like 4. What that means is that at various pHs in solution, these might or might not be protonated. In particular, it leads us to the realization that if we're looking at an example, well, let's look at a few. If we're looking at an example, we'll put this at about 5. If we're looking at an example at neutral pH, there's a fair chance that we're going to find our carboxylic acid group is going to be deprotonated and thus negative in charge, but that would mean that our amine group would likely at the same time be protonated and thus positively charged. However, those two compared against each other might imply that in this case the protein would have an overall charge of 0, even though the individual components might be charged. At a lower pH, this would be protonated, but now so would the carboxylic acid. And so the result might mean, for instance, in this case, that we had a net positive charge at a lower pH. Likewise, at higher pH, we might find that that amine is now deprotonated, making it neutral, while our carboxylic acid is still deprotonated. Meaning that at a higher pH, proteins are generally going to be found to have more negative charges. However, the precise nature of the protein structure, that is, the combination of different amino acids that formed into it, changes the particular combination. Each protein has a point at which the number of positive charges and negative charges balance out. At that point, the protein is electrically neutral. So that point is referred to as the isoelectric point. That difference in charge between various proteins at different pHs gives us an opportunity to potentially separate them. It can be somewhat challenging to separate proteins using some of the techniques that we've learned to separate materials in the past. In many cases, removing proteins from solution or trying to change their conditions too much, for instance with very high or low temperatures, can result in those proteins unfolding and losing the structure that makes them interesting to begin with. So, what a biochemist would really like as a tool is one that allows them to separate proteins without having to change the environment those proteins are experiencing from what they might normally approximately be in. One of the most valuable tools to do that is called gel electrophoresis. Gel electrophoresis relies on making a gel. There are all kinds of different materials that can make gels, but broadly think of a loosely knit together polymer of organic molecules. This gel is a material that the proteins cannot diffuse through on their own. So there are little wells at one end of the gel, and if a protein in solution is added into that well, that is, if it's deposited into the gel, it cannot diffuse through the gel. In a lot of common gel media, the spaces inside the gel, the little pores, are too small for proteins to get through on their own. So various proteins, for instance, the red and blue dots here, might represent wells with pure samples of a protein, while this black dot might represent a well with a mixture of proteins in it. They can't diffuse through on their own, but they have charges. So what's typically done is a voltage is applied across the gel. In essence, electric current is run through the gel. That electric current is going to pull on the proteins. But because the voltage is constant, the degree to which a protein is pulled through the gel depends on features like its charge. What that means is that a protein that might be relatively small with a relatively high charge could go quite a long way up through the gel. So it would be traveling this way, and at some time later, when the current is turned off, it might be found up here. By comparison, a less charged protein would travel less distance. Now, this both allows individual proteins to be characterized, but it's also very valuable in separating proteins that are otherwise going to be perhaps similar or mixed together. If a mixture is placed in this setting, it's going to separate based on charge. And this, by the way, is fairly analogous to the chromatography that we use to separate different kinds of chlorophyll in lab at the end of last semester. So let's say, for example, that this sample has just a little bit of the blue protein and a lot of the red protein. After running gel electrophoresis on it, it would be observed to have multiple bands. Each of those bands would be corresponding to one of these proteins, and typically the size or intensity of the band is at least somewhat related to the amount. At a later time, this material could be removed from the gel, and that purified protein could then be used. So this is an example of weak acids, weak bases, and buffers in action in a setting that is, in a sense, rather different. Ultimately, what I wanted you to see from this example is that the concepts we've learned about buffers can be applied in a wide variety of settings.